Hello, everyone. Thanks for attending this webinar. Today's webinar is titled on the metal insulator transition of vanadium oxide topped with tungsten thin films. That is going to be presented by Prof. Alain Gibault and Guillaume. Yeah, sorry about that. And Prof, the floor is yours. All right. Yeah. Switch on the microphone.
Maybe Mahmoud, if you allow me just to come in before Professor Gibault and Prof. will start their talk. First of all, fellows and colleagues, it's really a special honor to have with us Prof. Alain Gibault and Prof. Guillaume Vigneault with us here at Itamba Labs within the framework of the UNESCO-UNISA Africa Chair in Nanosciences and Nanotechnology. Both of them are, in particular, Prof. Alain Gibault is a senior associate to the UNESCO Chair, of course, and a long-term partner. We have a really robust cooperation between his group at the University of Le Mans, as well as with his capabilities in terms of material science, in particular, in general, and the synchrotron radiation facilities and large facilities such as neutron scattering. We are really delighted to have Prof. Alain Gibault as a special partner, and here now it is enriched with the presence of Prof. Guillaume Vigneault, also from the same region in France, with whom I hope we will also subscribe this cooperation in a very long term. Thank you so much for taking off your time, Prof. Alain Gibault and from Vigneault, and availing yourself to visit us in South Africa and to give us this talk. Thank you so much. Thanks a lot.
Thank you very much, Malik, for your very kind invitation to come here. And of course, it's always a great pleasure to be with all your students and to come here in Cape Town. And today we are going to discuss the metal insulator transition of vanadium oxide, which are doped with tungsten. And basically, this is a very long story. We started this a long time ago with Dr. Kanakana, who was here before you, maybe about 10 years ago or 20 years ago. I don't know. I cannot remember now. And he's now in Texas, having a very good position in hopefully in the near we will be able to do it as well. And he was asking us to look at those films with different techniques, and in particular, X-ray reflectivity, I will introduce this later on, and ellipsometry, because ellipsometry is really a very nice technique to look at the optical properties of thin films. And this is the technique to be used to look at the optical properties of thin films. So let's start. Yes, okay.
Second.
All right. So why do we want to study vanadium dioxide? So for those of you who know, I mean, this is going to be not very new for you, but for the one who don't know about vanadium dioxide, this is a very interesting material because basically it has a metal insulator phase transition. So what does it mean? It means that it goes from a metallic phase with a very high resistivity, like the one that you can see here. So the resistivity is very high, and when it's the insulator phase, And when it goes metallic, the resistivity goes down with a very large variation, several orders of magnitude between the insulating and a metallic phase. And the transition is occurring at about 68 degrees Celsius, and it is accompanied by a change in the structure, because you see in the insulating phase, you have a monoclinic structure, and when you go into the metallic phase, it goes into a tetragonal phase. So it's basically a change in the structure, which is also accompanied by a change in the electronic properties of the material. And so next, if you look at how this material is interesting, you will find that the optical properties are also changing with temperature. And this is quite interesting, especially because it has a thermochromic property that is extremely useful for doing, for instance, smart windows. And the other thing that people have been observing is that you can change this transition temperature of 68 degrees Celsius by doping with other materials. You can put donors like tungsten 6+, or acceptors like chromium 3+. And this is going to change the transition temperature. So you can either increase or decrease the transition temperature by doping VO2. And of course, I mean, applications of these materials is with smart windows. So how does it work? I will show you that if you are in the insulating phase, well, you can transmit the sunlight through windows on which you have put a vanadium dioxide film, and you can transmit the infrared radiation, while if you are in the metallic phase, because it's a metal, it's going to reflect the infrared radiation. And this is very interesting in many countries where when it's very hot, you don't want the light to go, especially the infrared light, to go through the windows. And it's also shown here on this graph here. You can see that if you look at the transmittance of, I don't know where is my, here it is. My pointer here, you see if you are at 20 degrees Celsius, you have a transmission of about 60% in the infrared region at 2000 nanometer, while if you are at 90 degrees Celsius, for instance, you can see that the transmittance is very low, about 10%. So you kill the infrared radiation in the metallic state, while you let the infrared radiation to go through the window if you are in the insulating phase. And so that's very interesting, except that it's very rare that your window is going to be at 90 degrees Celsius. So you want to adjust the transition temperature to close to room temperature. And this is going to be efficient if you are able to do that. Why it's also interesting? Because, of course, if you look at what's going on, human body is emitting infrared radiation at temperature of 36 degrees Celsius. And of course, if you can manage to measure this, then it's very useful, especially for the army. You can use infrared detectors and measure in this way the presence of people in the fields. And so that's interesting. Another application of vanadium dioxide is actuators. So you can use this because of the difference between, for instance, chromium in this case and vanadium dioxide. They don't have the same thermal expansion. And when vanadium dioxide goes through the transition, well, you can use this as actuators. and you can very easily use this in many cycles, like more than 10,000 cycles. And that's a very interesting story. And additionally, it can be used as metamaterials. So metamaterials are interesting materials because they can make the index of refraction, which are below 1 and negative. So typically here you see in this case, well, you can go negative into the index of refraction. And so, of course, I mean, vanadium dioxide is a very interesting material, but the key point is that it's interesting as a pure material, but at 68 degrees. But what we want to do is really to be able to use it at a lower temperature, close to room temperature. So how do we do that? Well, people have been looking at this type of materials with different doping agents. And you can see that, well, here there is a very nice PhD thesis, 2018, and they put a very nice diagram here where they have plotted the variation of transition temperature as a function of the percentage of the doping agent as a function also of the ionic radius. So you can see that, for instance, if you are using tungsten ions, they have a very similar ionic radius as vanadium. So it means that you are going to move along a constant ionic radius line like this. And you can see that depending on the type of ions that you are going to use, you can either increase the transition temperature or decrease it. So typically, if you use chromium, you see chromium is typically here, or well, gallium here, you increase the transition temperature. But if you use an electron donor like a tungsten 6+ or niobium 5+, well, you will niobium or which one? Molybdenum 5+, sorry. Then you will decrease the transition temperature. But you can also play with other ions. And if you modify the ionic radius, you can see that you can still decrease the transition temperature by putting larger ions with larger ionic radii, or you can increase the transition temperature by putting ions which have a smaller ionic radius. Okay, so in the following of this presentation, we are going to focus on the tungsten 6+ doping agent, because this is one of the most efficient ones to reduce the transition temperature. Okay, and well, the films we are not making them in Le Mans. They were made at the Commissariat at Energy Atomic in CEA, Le Repos, France, by pulse magnetron deposition. And they were using a vanadium target and a tungsten target, and working in an argon-oxygen atmosphere, so that they were able to produce some films. And how did they manage to make the doping? By making multi-layers. So they were depositing vanadium in oxygen atmosphere, so that this was transforming into vanadium oxide, and then tungsten, and then vanadium, and so on. And then the next step was to anneal those materials at 450 degrees Celsius, so that there was a diffusion of tungsten into vanadium oxide. And in the end, we were observing a thin film, well, which was normally homogeneous in terms of the repartition of tungsten inside the vanadium dioxide. And so objectives of this study was to study the influence of tungsten doping on the physical properties of vanadium dioxide thin films, determining the structural and optical properties. And how do we do that? We did several types of measurements, X-ray diffraction measurements, X-ray reflectivity analysis of the thin films, and then finally, optical measurements by using ellipsometry measurements. Okay? And the first thing is that if you do X-ray diffraction, you are going to look at how the structure is evolving as a function of temperature. So you will get the lattice parameters. And if you look carefully at how the Bragg reflections are evolving, you can describe the hysteresis that you can find in this transition. The reflectivity analysis is very interesting for measuring the morphology of the film and typically the thickness of the deposited layer and the roughness of the interfaces. And the ellipsometric analysis, well, when you do that, you will get information about the refractive index, typically the real part of the refractive index N, and its imaginary part, which is K, which is, well, related to the absorption of light. If you want to understand the absorption, you need really to understand what is the K value of the index of refraction. And you will see that once you have done that, you can begin to do some very smart analysis of the dielectric functions that you can get from the index of refraction. And then you will be able to find some information about the bond structure of the tungsten dioxide. So let's see how we are going to solve the problem. In ellipsometric spectroscopy, as Guillaume is going to show you, one major concern is, well, the fact that if you really want to get the good information, you need to discriminate between the index of refraction and the thickness of the film. And if you don't know very well the thickness of the film, then that's going to be very difficult to get a good estimation of the index of refraction, of the refractive index. So what we do X-ray reflectivity measurements. We measure the thickness, and once you have done that, you can determine by ellipsometric spectroscopy the refractive index of the material. Okay, fine. So I'll start with the X-ray diffraction analysis. So you make a film, and then you use X-ray diffraction in normal way. That is to say, you are going to make a theta to theta experiment. You shine the X-ray beam at a theta angle. You put the detector at a 2 theta, and you measure the diffracted intensity as a function of the 2 theta angle. And you can do this in Le Mans. We have a diffractometer which is equipped with a nice cells, which is made with the Peltier system. And with the Peltier system, you can cool or you can heat the film very precisely with a precision of less than 0.1 of a degree Celsius. And so you can do the evolution as a function of temperature, like this. And if you do the theta to theta scan in the insulating phase and in the metallic phase, you will see that there will be a little bit of a difference. So typically, you can see that the major difference that you can observe when you go from low temperature to high temperature is that this peak is shifting. And actually, if you try to calculate it, you will find out that you go from the monoclinic phase at room temperature into the rutile phase at high temperature at, in this case, 85 degrees Celsius. And so then you would say, okay, fine, we see some differences. Fine, we know that there is a transition. Can we do it a bit better? Yes, we can do it a bit better by doing the analysis of the diffraction diagrams using mode program. So last time I was here, I was introducing this type of material analysis technique, the mode Rietveld analysis. And that's what we were doing here. And you can see that at 25 degrees, we can calculate completely the full 2D pattern, diffraction pattern of the VO2. And we can do the same at 85 degrees Celsius. And in the end, we get information about the lattice parameters corresponding to the structure. So typically, you see, if you look at the literature, you will find CIF files for the monoclinic structure of VO2, and the same tetragonal in the tetragonal phase. And we can calculate, and you can see that there is not a big difference between the calculated lattice parameters that we made with our fields and the one from the CIF file. Fortunately. Otherwise, we could say that there was a problem, but this is the type of information that you can get. And additionally, once you have done that, well, you can look at, if let's go back to this one. You can, no, this one, you can look at how you go from the 011 monoclinic reflection to the 110 radial reflection. Okay? So you measure this as a function of temperature, and you look how this 011 reflection is shifting towards the 110 reflection of the rutile phase. So when you do that, you can see that, well, typically this was measured, I cannot remember what was the temperature here, but it was intermediate. So you can see that at a certain stage, the system is passing from the rutile phase to the monoclinic phase. And at this specific temperature, there is a coexistence of the two phases. Okay? So you can see that basically, if you look at the shape of the reflection, the shape of this reflection cannot be described by only one line shape. You have to put two line shapes, and one is related to the monoclinic phase, the other one is related to the rutile phase. And if you do this in a better way, I mean, you see here, we are increasing the temperature here. So there is only one reflection here. And in this area, you see the coexistence of two reflections, and then there is only one, which is a rutile one. And why do you see something like this? Because it's a first order transition. And in a first order transition, you have a coexistence of two phases. And if you look at the intensity of both reflections by fitting those reflections as with a Gaussian function, for instance, you can calculate the percentage of the monoclinic phase as a function of temperature. And that's what we did here. And you can see that, well, if you heat the film, the transition is occurring at around 74 degrees Celsius, while on cooling, the transition is occurring at 65 degrees Celsius. So there is an hysteresis that you can find in the diffraction experiments, but you can see also this if you measure the resistivity of the films. You will see also that you will find an hysteresis. Okay, and so you do that for different concentration of tungsten. We went from pure VO2 to 3% of tungsten, and you can see that when you increase the concentration of tungsten, well, you decrease the transition temperature. And in this case, we were able to decrease it by about something like 30 degrees Celsius. And so now we are very close to room temperature. So it means that the tungsten is quite efficient to reduce the transition temperature. If you look at the literature, you will find that people are observing very different variation of this transition temperature, depending on the tungsten concentration. I don't want to go too much into the details, but this is what we have found here. And then we did the reflectivity. And just to give you an insight of what is reflectivity, you shine the X-ray beam at very shallow angle, you measure the reflected intensity, and the reflectivity is just the ratio of the reflected intensity divided by the incident one. So this is something which is always less than 1. It's 1 if you totally reflect the beam, and then it goes down, and you can totally reflect the beam at low angle. So just to show you what it is, you see, you can either describe it as a function of theta or as a function of the Q-wave vector transfer, which is 4 pi sine theta over lambda. And when you do that, if you do it on just silicon, what you will see is, you see the reflectivity is close to 1 at very shallow angle here. It's 1 here. And then it's decaying very quickly, several orders of magnitude, as a function of a very small variation of the angle or of the Q-wave vector transfer. And so you can see that it's decaying as 1 over Q to the 4th. That's a very, very sharp decay. And now, if you put a thin film on top of a substrate, what's going to happen is that you are going to both reflect at the top surface here. This ray is reflected here, but part of the ray is going to be transmitted in the film, reflected at the interface with the substrate, and the two rays which are going to go out, they are going to interfere. So what's going to happen is that instead of seeing a reflectivity like a smooth decay, you will see some fringes. And the fringes, they are related to the thickness of the film. So typically, those are known as the Kissick fringes, and the separation between two fringes is just related to the inverse of the thickness. So if you measure the distance between two fringes, well, you have direct evidence of the thickness of the film. And so if you look at that, you see if you have a large thickness, the fringes are going to be very next to each other. But if you have a very small thickness, well, the fringes, they are going to be very much separated. Okay? So this is a story about reflectivity. You can calculate this very well. And that's what we did here. And you can see that if you look at 25 degrees, what is the reflectivity of the film, you see very well the Kissick fringes. And then I didn't speak about that, but the fact that you don't see the fringes at IQ is related to the roughness of the film. So if you increase the roughness, you will decrease, well, the observation of the fringes. And so this is what we see here. You can see that we see very well the fringes up to here, and then all of a sudden, well, you don't see them because of the roughness of the film. And this is done in the electron density profile. So you know what is the electron density of the silicon. You know what is the one of the vanadium dioxide. And you can see that the profile does not go sharp at the end. It's quite rounded, and it's rounded because of the roughness of the film. Okay. But what we learned in doing those reflectivity measurements at low and high temperature was that the film thickness was not evolving much. So you could keep it almost constant. You see it's 71.5 at 25 degrees, and it's 7.1.6 at 85. No change at all, almost. So it means that although you have a phase transition, in this case, we don't see much of a difference between, well, the two thicknesses at low and high temperature. So that was a story about well, determination of the thickness of the film. And that's a very important story, because then in ellipsometric measurements, it means that we can keep the thickness constant. And you will see that the thickness is a very important parameter. And now I will talk to you. So you will explain now ellipsometric.
Yeah, okay. As Professor Maza asked me, I would like to explain a bit the principles of ellipsometric measurement. Okay, the device is composed of a source. In fact, this is a xenon lamp with a spectrum which goes from UV to infrared. It means that the source is polychromatic. And the incident beam goes through a polarizer, which transforms the light into a linearly polarized light. And then the beam is reflected on the sample. at this when during the reflection, the samples induce a phase change, and this will change the polarization of the reflected beam. In fact, we have an elliptic polarization after the reflection. And this polarization, this elliptic polarization depends, of course, of the samples that you are studying. By analyzing this elliptic polarization, the device can deduce two ellipsometric angles called psi and delta, where delta is linked to the relative change in phase, and the psi is linked to the relative amplitude change during the reflection. Okay, then during a measurement of ellipsometry, you will have a set of psi and delta at each wavelength. Okay, and this psi and delta depends of the change in polarization, which depends of the samples that you are studying. Ellipsometry is an optical technique based on the analysis of the change in the state of polarization of light after its reflections on a sample. The next question is how to analyze the measurement. This is another story. Okay, to analyze this data, here you can see the measured data with the psi and delta, the angle, the ellipsometric angle. And from these ellipsometric angles, you can calculate, thanks to the ellipsometric equation, the experimental ρ, which is equal to tangent psi exponential I delta. This is an experimental term here, but this experimental term is also equal to the theoretical term, which is the ratio of Rp to Rs, where Rp is the Fresnel equation for the reflections when the field is parallel to the plane of incidence. On Rs, this is the one where the electric field is perpendicular to the plane of incidence. Okay, to be able to calculate the theoretical ρ, we need to define the model. Here, the model is composed of silicon substrate with VO2 layer with a thickness h and optical properties defined by N and K. N, this is a real part of the refractive index, and K, the extension coefficients linked to the absorption. This is the imaginary part of the refractive index. Then, with the ellipsometry, we are able to calculate, to define the thickness h and the refractive index of the VO2 layer as a function of the wavelength. Okay, sorry for the questions. In the standard data analysis, to calculate this ratio, we need to know the Fresnel. We use, in fact, the Fresnel equation for reflection. And you see the incident beam. In the incident beam, you have a first reflections at the interface, at the free surface, at the interface 0, 1, 0 for air and 1 for VO2. And the beam goes through the layer, and there is another reflection at the interface 1, 2, between the film and the substrate. And in fact, the total reflected beam is equal to R01, which is the reflection at the first interface, plus R12, which is the reflection at the second interface. But you have to multiply it by a phase shift because the beam here goes through the layer. This phase shift is defined by exponential minus G2 beta, where beta depends of h, the thickness of the film, and N1 and K1, the refractive index of the VO2. Okay, now we have to calculate this for all the wavelengths of the source. Then to do that, we need to know how the refractive index evolves as a function of the wavelength. To do that, we have to define a dispersion function to modelize this evolution as a function of the wavelength. As there is a direct link between the dielectric function and the refractive index, we define here a dielectric function with two terms. One term name called the Lorentz term, which take in account the transition between the band energy, and a second term, a Drude term, which take in account the free electron, the part of the conductive part of the samples. Okay, donc, according to the temperature of the samples, they will use the first part at ambient temperature at 25 degrees, but at high temperature, we need to also use this second term because the samples become conductor. Then, to summarize the standard data analysis, first, you make a measurement of C and delta. Then you can calculate the experimental rho equal to tangent C exponential EI delta. And you have several unknowns, which are the parameter which defines the evolutions of NK. You need to model your samples, and then when you do that, you can calculate the theoretical rho, which is the ratio of RP to RS at all wavelengths at the same time, with reflectivity, Fresnel reflectivity, and you need to choose a dispersion law to know how the refractive index evolves with wavelengths. And then you fit the data, you fit the parameters to minimize the difference between the theoretical rho and the experimental rho, and you find the correct n lambda and h, the thickness. Okay, this is the standard data analysis. In fact, the problem with this standard data analysis is that, particularly for the VO2, you can have a correlation between the thickness and the refractive index, because the film is there is absorbing the film, questioning the uniqueness of the obtained result. And secondly, the choice of a dispersion law for model n lambda can influence the fit and also the calculated refractive index. Then we have tried a new method called the point-by-point method, where we have only two unknowns, n and k, the real part and the imaginary part of the refractive index, and thickness is known. Thickness is known because we need the X-ray reflectivity on the samples, and we extract the thickness from this technique. Then the advantage of this approach, of course, there is no correlation between D and the refractive index, and also you don't need to define the dispersion function, because the problem to define the dispersion function, this function depends of the samples that you are studying. And for example, if it is polymer film, if it is insulator, semiconductor, or conductor, this is not the same law to describe the evolution of the refractive index. This is not the same law, and it's sometimes difficult to know what is the best law to define the samples. In particular with VO2, because sometimes you have a mixed coexistence of two phases, of two structures, the monoclinic and rutile phase, and it's difficult to say what is the best dispersion function. Okay, then in the point-by-point method, the advantage is first you measure C and delta, as the previous method. You calculate also the experimental load. This is the same method. You define also, you still define the model for the samples, and then you calculate the ratio, but you calculate the ratio for one wavelength at a time, and you obtain the corresponding N on K without a dispersion law. Okay, at each for each point, each wavelength, you make a fit, and you obtain the value of N on K. Then there is no correlation, and also there is no dispersion law to define. This is the advantage of this approach. And at the end, you have reliables, thank you, refractive index. Then here we can compare the refractive index and the extension coefficient of K obtained from the two methods on a pure VO2 film. Okay, we can see here there is not a big difference. And also, one may think that the two methods are very similar, and this is true for this case. But we will see that for the doped, tungsten doped VO2, this is completely different, and there will be a strong difference. On this also, we can see that the extension coefficient K of the samples at 25 degrees, there is absorption in the UV, and the film is almost transparent, invisible on the infrared range. But if the temperature is increased to 85 degrees, there is a strong increase of the absorptions defined by K, of the strong absorption, strong increase of absorption, which means that the samples become a conductor, and most of the incident beam is reflected.
Okay, I will continue. Okay, so you have probably seen that, well, learning about ellipsometry is a bit tough. Just one comment about what Guillaume was saying. You could see that analyzing the ellipsometry or the X-ray reflectivity is exactly the same formalism. And basically, all is defined by the Fresnel equations. So if you really want to understand how an electromagnetic wave is reflected on a surface, you need to understand the Fresnel equation. So, and this is valid for all the waves, X-rays, infrared, visible, whatever you want. This is the same formalism, okay? And so you need to learn about that if you want to understand properly the ellipsometry and the reflectivity, X-ray reflectivity. So now I'm going to comment about the results. And the first thing that I want to comment is the imaginary part of the dielectric function. So there is a very well-known relationship between the dielectric function and the index of refraction. So Guillaume has shown you that you can get out of ellipsometric measurements N and K. Okay, and so then if you take this complex quantity, you square it, then you will get the dielectric function of the film. Okay. And so this is what we did. So we can use this relationship, and once you have used this relationship, you can extract the imaginary part of the dielectric function. And this imaginary part of the dielectric function, you can see that it's evolving quite differently if you are at room temperature or in the metallic phase. Okay. So let's start with the room temperature. It's a blue curve. So what do you see in the blue curve? You see that, well, it starts at very low values, and then it's increasing. There is a big bump here. And if you look at this part and you put a straight line like this, you will see that the straight line is cutting the energy axis at a specific value. So this is in electron volts. So instead of working in as a function of the frequency, here we work as a function of energy, and this is 0.5 electron volt. So what is 0.5 electron volt? In the case of VO2, it's just the gap between the valence band and the conductive band. Okay? And this is what you get immediately from the measurements of the dielectric function. Okay? So that's one thing. And then there are several bumps that I'm going to explain later on. And now if you go at 85 degrees, you are now in a material which is no more an insulator, but it has a metallic behavior. Okay? So what's happening? You see that instead of having something which goes to 0 here, there is a big intensity in the imaginary part of the dielectric function. And this is related to what we call the Drude component. So if you take free electrons in a metal, the free electrons response of a metal is described by what we call the Drude model. And the Drude model is giving you something which has a very long tail like this and very intense at very low energy. Okay? And so if you want to describe properly now the imaginary part of the dielectric function, you need to model it. So how do you model it? Well, if it's in the metallic phase, you put the Drude component. And you can see the Drude component is this guy. So with a plasma frequency, which is omega p square here, this is something which is related to the absorption, gamma d here. And this component is going to give you this tail here. See this one, this big tail is just described by this function. Okay. But now if you look at what you get in the dielectric function, imaginary part, you can see that there is not only a tail, but there are many humps. Okay. And those many humps, you can ask yourself how they are related to your VO2. So then you need to describe those humps. And those humps, they are described by what we call the Toc-Lorentz oscillators. And those Toc-Lorentz oscillators, you see that they can be described by this function. It's a bit complex, but you need to understand what you have inside this, this type of function. You have, if you are in the insulator phase, a gap, Eg. So Eg is this one. So it's appearing here in this expression. And then you can see that here there is a specific energy, which is called EI, I going from 0 to n, number of oscillators you are going to put. And this EI here is the location where you are going to get the bump. And it has a given width and a given amplitude. And so if you look at how we deal with this, in the red one, you can see that here there is one bump, another one here. And well, that's the red one. For the blue one, there is 1 year, 1 year, 1 year, 1 year to describe totally the dielectric function. So you fit that with those Toc-Lorentz oscillators, you get specific values. And from those specific values, then you can say, oh, how is the bond structure of the material? And you see here that typically when you do the fit in the insulating phase, you get a gap value of the order of 0.6 electron volt. But additionally, from all the position of the bumps, you get other values, and those values are related to the transition, the interband transition between the electrons coming from the D band of the vanadium and from the sigma and pi bonds of the oxygen. Okay, and so you can fully describe what's going on in terms of energy into your material. Okay? And in the literature, you will not find so many people who have been doing a very careful analysis of the bond structure. Some people, they say, okay, I see that there is a peak here at 3, so I will put something like 3 here. But they don't do the calculation. It's very amazing, but that's the way it's done. And if you go into now the metallic structure, because you are in the metallic structure, it means that the Fermi level is located in the top part of the conducting bond, and you don't have any more gap. So Eg is going to be 0. So you destroy the gap of the semiconductor, and you can calculate also the different transition from the different levels inside the material. So this is why you see, once you have done the ellipsometric measurements, you can really get, first of all, the index of refraction, the refractive index of the material, but additionally, you can get the dielectric function of the material. And from the dielectric function, you can get very good information about where are located the energies in the material. So, and then you can also calculate the real part of the dielectric function. And again, this part is related to the truth, and this part is a bit complex to calculate. It's related to how you can calculate the imaginary part, the real part from the imaginary part of the dielectric function. So we did the calculation. Well, you have to do it. And then you get something like this. And you see definitely that if you look at the real part of the dielectric function, it's very different. You go negative into the real part of the dielectric function. Why that? Because you see here that the drude is negative. This is positive, but there is a minus sign in the front. And the drude is going to give you some negative component to which you will add this quantity and this one, and in the end, you will get something like this. So it's really typical of what you will see if you have a conductive material, a metallic material. If you are in an insulating phase, you can see that the real part is always positive. So fine, we understand what's going on in the pure. Now we want to see what's going to happen if we dope the material. And if we dope the material, that's what we get. So real part, you see, with point-by-point technique, with the standard method, while point-by-point is the markers, and the other line, the full line, is defining the standard method. For pure, very similar. For 0.7%, very similar. For 1.8%, you begin to see a discrepancy. And for 3%, it's completely different. Okay? So it's telling you that if you try to put a description of the refractive index by the standard method, if by any chance you have a mixture of phase, or you go, you think that you are in an insulating phase, but you are in a metallic one, then you are completely wrong. And typically, you can see that if you do the point-by-point method, you can see that here it becomes negative in the real part of epsilon, meaning that at 3% at room temperature, you are in a metallic, there is a metallic component into your material. And also, you believe that you are in an insulating phase, because normally the transition was found around 40 degrees Celsius. So if you are at 25, you would say, oh, I'm safe. I've gone through the transition. This is now an insulating phase, but the ellipsometry is telling you that this is not the case. And diffraction is also telling you that. I didn't comment it, but actually you never reach a full percentage of the monoclinic phase. You always have a mixture of monoclinic and rutile phase if you are doping with tungsten at a high level. Okay. So that's what we did. And then, well, you can see that if you look at 25°, the real part of the dielectric function, well, is evolving like this. In the case of the 3%, well, it's evolving like that. And we can calculate this with the Toc-Lorentz and Drude model. Now the full line here are calculation of the dielectric component. Okay? And you can see that in the imaginary part, for the 3% at 25°, there is also a very nice Drude tail, which is not occurring here. And depending on the doping concentration, this is pure. So you see the gap here is at 0.5. If you go to 0.7, it's going to be close to 0. And if you go at 1.7% of doping, you can see that the gap is almost negative. So it means that even at 1.7% of doping, you begin to be, well, at room temperature, at a level where you are almost conductive. Okay? You kill the gap. Okay? And of course, if you go at 85°, everything is consistent with a metallic structure. You see it very well in the real part of the dielectric function, and also very well in the imaginary part. So because of this big tail, the Drude component of the dielectric function. Okay, and so conclusion now, well, I hope that we have convinced you that with the doping with tungsten, we can decrease the transition temperature, and above all, that if you use combined techniques like X-ray diffraction, reflectivity measurements, ellipsometric measurements, you can get very good quantitative information about what's going on in your field. But there is a price to pay every time. Don't think that, well, you will get it like this. You will have to do some calculations and go through the theory. Otherwise, you cannot understand what's going on. And of course, this work has been done in collaboration with many people. Especially, we need to thank Abdelaziz. He was a master student with the two of us, and he started doing those measurements and beginning the analysis. Those two people, they are the ones who are making the film. This is someone also who is now the supervisor of Abdelaziz. Mohamed Shekhar, you know him.
He's also attended.
Yes, yes. And Malik Bazar, I'm sure you know him as well. Thank you for your attention.
Yeah, it's time for question. Prof. Maza, please unmute yourself.
Thanks a lot, Prof. Guillaume and Prof. Alain Gibault for the outstanding and inspiring indeed study of this VO2 and a complete description of the various phenomena that I must admit, in particular, the band gap description is more accurate and highly justified, as you correctly highlighted. I have just one question, is that generally speaking, the VO2 has different, of course, has quite a number of polymorphs. And in a thin film, being deposited by any type of technique has always a mixture of these polymorphs. In your case here, what is the purity of the VO2? Is it a pure, how can I say, the rutile type phase, or is it a mixture? That's one. And the second is that we are very well aware that in this kind of VO2 thin films, there is always some grains under huge strain. Have you observed that with the X-rays so far? Thank you.
Yes, so the first question, I mean, from the data analysis that we made with MODE, we found out that it's perfectly consistent with the rutile structure. And in addition, there is no specific orientation of the VO2 when you are using the sputtering deposition technique like this. So you make grains which are randomly distributed in the film and randomly oriented. This is why we didn't have to put any type of preferred orientation in the calculation. So it means that on the contrary to what you could observe when you do deposition by a molecular beam epitaxy or maybe by pulse laser deposition, where you could have some specific orientation of the film. In this case, it's not true. Of course, because there is no specific orientation, the strain in the material is quite small compared to what you could get if you were having a very high preferred orientation. So typically, we were calculating this using MODE, and there is not much strain, and there is no preferred orientation, so that we could calculate very well the scattering, the diffraction pattern in both cases, both in the case of the insulating phase or the metallic phase.
Thank you so much. Thanks a lot.
Yeah. Professor, close yours, please.
Okay.
Oh, easy.
Bonjour, bonjour Alain.
Somewhere in Canada.
Bonjour Alain, bonjour Guillaume. Oui, je me suis réveillé très tôt pour ça, pour avoir le plaisir de regarder cette excellente, this very interesting talk. So thank you Alain, thank you Guillaume for this superb talk. I learned a lot concerning l'ellipsométrie this morning. So, comme on dit chez nous au Québec, je dormirai moins niaiseux ce soir. Donc, so I'm going to ask something which is related to the tungsten dop, because in fact, the way that you are obtaining this doping is by diffusion of the tungsten. So usually, the tungsten is substitutional. So I mean that tungsten is replacing the vanadium atoms, and sometimes also which happens is that you can create clusters of tungsten. So do you think that the method of doping could influence the results, because then you can have, for example, maybe a non-uniformity doping as a function of the thickness or something like this? Then maybe then you can have a difficulty to modelize something which is not just uniform doping. And for example, if you compare with other technique that the doping is done at the same time than the synthesis, not by diffusion, but during the synthesis, do you think that the result could be different?
Yeah, it's a very good point. It's clear that when you are doing it like this, you could have maybe in some places some clusters of tungsten, and it's not very clear whether it is really very well uniformly distributed. Although, well, when you look at the X-ray diffraction pattern, there is no specific sign of having metallic clusters of tungsten. We could, well, wonder if they were. Normally, you should be able to see some of them, unless they are very small. But in this case, we didn't see any specific contribution of tungsten into the scattering pattern, and it is impossible from a very low concentration of tungsten to calculate from the diffraction pattern the content of tungsten in the films. This is too small content of tungsten. But well, what is really clear is that it's very amazing in this case that when you measure the transition temperature let's say by diffraction or by other techniques, you find out that the transition temperature for instance, for the 3% is 40 degrees Celsius. But at 25, there is a very strong contribution of the metallic behavior. So this is probably also related to the fact that maybe in the films, there are areas where there are metallic clusters which are surrounded by isolating parts in the film. This is the way we understand what's going on in this film at the moment. So yes, you are right. I think probably in this case, when you do the diffusion, it is very likely that the system is not completely homogeneous.
Okay, merci. Thank you very much, Alain. And et bon séjour dans cette merveilleuse ville qui s'appelle Cape Town. Et j'espère que la prochaine fois, on y sera ensemble.
Hopefully, I mean,
Okay.
come in February, we will be there.
Yeah. So I think my student is going to ask a question because he did a lot of ellipsometry with our VO2. I'm going to let him. Okay, bye. So bye-bye now.
Bye.
Hi, thank you for the presentation. I found it very interesting. If my questions are silly, I'm going to blame it on the time of day in Quebec rather than my lack of knowledge.
Well, that's no silly question, you know.
Well, in that case, I have plenty. You mentioned that different models can be used for different types of materials and they will provide a more physical fit of the thin film. I was wondering if you could explain why the Toc-Lorentz and the Lorentz-Goshen models are the ones you used in the article you published this year for the VO2 and doped VO2 in both phases.
Yes. So first of all, I mean, if you look at what's going on in the ellipsometric measurements, the usual way of calculating the index of refraction is to use a Drude-Lorentz model. So this is what was sorry, I'm trying to the computer is stuck. I don't know why it's stuck. Okay. Pretty good. Yes. Yeah, so you see here in this case, one way of describing the index of refraction would be to use this type of model in which you consider that you have, for the Drude component, 3 electrons. And here, this is typically what you can get for oscillators with energies in the infrared range. Okay, so this is what people are usually taking. But as Guillaume was mentioning, the main problem with this is that if you don't know really the good way of describing the index of refraction, well, then this Drude-Lorentz model is not very adequate. And so the story which was pointed out by one of the referees, when we had we wanted to publish this paper, the referee said, well, you should not do that. You should do the point-by-point method. And the point-by-point method is indeed a very good method because you don't need to describe how the index of refraction is changing as a function of wavelengths. You just have 2 measurements, delta and psi, and you have 2 unknowns, which are n and k. And with 2 measurements and 2 unknowns, there is only one possibility to get n and k. So this is why, I mean, when we looked at what he was saying, we said, okay, maybe we should do what he's saying. Should be better. And so we did that. It took us a little bit of time to understand the point-by-point method, but nonetheless, we did it. And in the end, you can see that it was extremely relevant, because if for pure VO2, there is not much of a difference, if you go into doped materials, you can see that the standard technique does not give you the right answer. So it's much better to use the point-by-point method. And then, if I understood correctly your question, then you were asking, why do we use this?
Yes.
So why do we use this? Because you see, when you try to understand what is the shape of those bumps, you find out that they have a kind of a Lorentz description. So it's a Lorentzian shape. And basically, the top Lorentz oscillators are the best oscillators to fit those data sets. So this is why we use this one. And additionally, the top Lorentz oscillator, they are very interesting because you see that there is a description of the top Lorentz oscillator for the imaginary part. And then if you want to calculate the real part, this one, there is an analytical expression for the real part. So this integral, you can calculate it, and there is an analytical expression for this real part. We didn't put it because it's very lengthy, but you can fully calculate the imaginary, the real part, once you have used the top Lorentz. In some cases, you can see here that the top Lorentz does not describe extremely well this part, because the Lorentz shape is quite extended, and you could use a top Gauss oscillator, but the top Gauss oscillator, you cannot calculate the real part in an analytical way. So this is why we use the top Lorentz oscillators. But the top Gauss, there is no analytical expression for the real part of the dielectric function. So I hope that I was answering your question.
Yes, thank you. If I may ask another question, concerning the point-by-point fits, would you advise to go from the longest or the shortest wavelengths in particular, or does it depend on your starting point that you got from the Lorentz-Drude model, or is it really irrelevant?
Yeah, you have to be careful with the point by point, because it depends of the initial point where you start the measurement. And in fact, what we did, we take the point from the Lorentz fit, and after we did the point by point. And there is another possible problem, is the roughness of the sample. Because in the point-by-point model, we did not take into account the roughness, but we check that this is not a problem before to do the analyze. Okay, but you're right. The starting point are very important, because otherwise you can have stuck in a local minimum during the fit. You need to be careful with the initial parameter.
Okay, thank you. I maybe have a last question. You mentioned the correlation between the thickness and the optical constants, and I was wondering, because you fixed the thickness from XRR measurements, can you still use this model to accurately determine the thickness of different samples which have a different thickness, as long as they're close enough so that the optical constant doesn't change too much? And if you did, I've read about there being that the VO2 isn't sensitive to the thickness in the low temperature phase, but it is sensitive in the high temperature phase. Have you done any measurements on that? Could you confirm that information? Don't know if I was clear enough, but.
Yes, well, we did the reflectivity measurements in the high temperature phase, and both in the low and the high temperature phases. And we found out that the thickness was not changing much in this case, because typically those films, they are quite thin. They are some of the order of 70 nanometer. So with the value of the temperature, how do you call that?
In fact, the thickness increased by 1 nanometer at high temperature.
Even less, yeah, even less. Yeah,
Like
Yeah,
1 or 2 nanometer.
And just also to give you more information about the point by point, if you put the wrong thickness, you will not get it right. And the point by point is also very interesting because since you are getting the N and K values for each wavelength, if you make a mistake, you will not get a smooth curve for N and K. You will get some kinks inside the the calculated N and K, and sometimes, I mean, it's completely crazy. And so we tested that, and we are playing a little bit with changing the thickness of the film, and it's very sensitive also in the point by point method. But to come back to your question, yes, we measured the thickness in both phases. And there was not a big difference between the two thicknesses. Yeah.
Sorry,
So,
I have a question related to this. So when you calculate the thickness at different temperature, you see that the thickness is almost the same, while we have in two different phases. One of them is monoclinic, the other one is tetragonal.
Yes.
So it means that the volume actually doesn't change when you go from one phase to another phase. And is that the reason that you see the peak in XRD at the same two theta?
That's correct. Actually, I mean, if you are not very careful, you can describe the monoclinic phase by a reticle phase, almost.
Because the peaks were very, very close together.
They are very close to each other. But if you go back to here, you see, apparently there is a big change in the volume, because the volume of the monoclinic is almost 120 angstrom cube, and the other one is 59. Except that there is a doubling of the parameter, of one of the parameters, and it means that typically, if you double the volume of the tetragonal, you get almost the volume of the monoclinic. So there is not a very big change in terms of volume modifications when you go from the monoclinic to the tetragonal phase. And this is why, indeed, there is not a big change in the thickness. Okay.
So another question, maybe a stupid in experimental point of view, but when you do doping experimentally, do you have control on the percentage of doping, or you just dope and then you measure?
No, I mean, as I was saying, we were not the one who were making the films. They were made at the CEA, and those guys, they made very careful experiments to measure the exact content of the doping by Rutherford backstretching. So you can measure very accurately the content of the doped films. And in this case, for instance, for the 3%, they measured 2.7%, okay, slightly less. But we have exactly the right values. But yeah, they were controlling very well the amount of doping. And in a quantitative way, while in many cases, some people, they say, well, I dope, I have 3%, but they don't know exactly how much the right content of the percentage is.
Okay. So another stupid fundamental question. So what is the reason of this lowering the temperature when you dope with tungsten? What happened?
Yes.
Fundamentally. And then from experimental point of view, you compare your experiment with some model, and then you somehow, I don't know, should I say calculate or fit? Yeah. By fitting, you find some energy levels, electronic structure of your system. Have you calculated with some more fundamental model like DFT
Yes.
calculation?
Yeah. So basically, when you are going to put some tungsten into the VO2, you are going to modify the environment of the vanadium oxygen atoms. And basically, what's happening is that once you are going to put tungsten inside, you change the energy levels, the bound energy levels of the dope materials. And if you put too much tungsten, by changing the environment of the vanadium atoms, which are substituted by the tungsten, you end up with something which becomes metallic. Yes. So you change really the distances between vanadium and oxygen, and this change in distances is, well, typically one of the reasons for which you get some transition in vanadium dioxide.
So does it distort the whole structure? I mean, does it distort the whole like this when you add 3% of tungsten, or just?
Yeah, it's distorting the lattice. I mean, you don't have the same type of distortion when you replace vanadium by tungsten that if you just have pure vanadium oxide. But we didn't make any DFT calculations. That's not our field. But if you want to do it, I mean, that's fine. I mean, go ahead.
Interesting.
Sure, I'm sure it will be interesting. I mean, you can try and see what's going to happen. I think some people have already done that, but yeah, go ahead.
What's the transition temperature of the 3% dose?
Sorry?
Roughly the transition temperature for the 3% dose.
For the 3%, we went down to 40 degrees Celsius. 40.
If the optical properties are explaining that when you dope it, you kind of have mixture of both metallic and rutile, isn't that going to at least explain like the threshold of the dopant content that you need to decrease the transition?
Yeah, well, actually, I mean, it's interesting to look at what's going on with the diffraction experiment. Where is it? I didn't put it, or what? Yes, here. So you see, if you look at this graph here, it's my pointer here. This graph, you see, you get the percentage of the monoclinic phase in the material. And if you look at the pure VO2, you see that you go from 0% to 100% of the monoclinic phase by using the calculation of the position of the intensity of the 110 and 011 Bragg reflections. But if you do it for 3%, you see that for 3%, you never go at 0% at high temperature, and you never go at 100% monoclinic phase when you are at low temperature. So it means that if you look carefully at this diagram, at let's say 25 degrees, you have only 80% of the monoclinic phase. So 20% is still remaining in a metallic phase. That's what we understand from this diagram, what is going on. And the further you are doping, well, the less pure you get the monoclinic phase. So this is explaining in some sense what's going on, and you can see also that it's become less sharp. The transition is more rounded when you increase the doping content than if it's pure.
Oh, okay.
Okay, Chris, please ask your question. Chris? Okay, so please ask your question.
Did you say Benedict? Sorry.
Yes.
Okay, perfect. Thanks. I just wanted to. I don't think I was very clear on my last question. I wanted to repeat it in different terms. I was wondering. I understand that you fixed the thickness with XRR measurements in order to determine N and K. I wondered if you then did the exercise in the other way around for other thicknesses and used the N and K in order to determine the thickness, because you mentioned that there was a correlation between the thickness and the optical constants. And so I wondered if for different thicknesses, you could still get an accurate measurement of the thickness by ellipsometry, or if it's no longer possible because of the correlation. And if you could get an accurate measurement, I wondered if this was the case for both phases or only for the rutile phase. So I think in Sun's article, she mentions that the low temperature phase isn't sensitive to the thickness for ellipsometric measurements.
No, I think the main problem is that if you know very well N and K, I am sure that you will be able to get the thickness out of the measurements by ellipsometry, if you have a very good knowledge of it. If you don't have it, you always end up with a correlation between the two the two values, or the three values, N, K, and H, and that's going to be difficult. So that the very best is definitely to be able to measure the thickness before and then do the ellipsometric measurements. And in many cases, well, it depends what type of films you are making, because in this case, we were asking for thin films, typically of the order of less than 100 nanometer. Of course, some people, they are making much thicker films, and then it's very difficult to get the thickness from reflectivity measurements, because then you don't see the fringes, and well, it's a problem. But well, there is no reason for which you should not get the thickness if you know perfectly well the index of refraction, the refractive index. But the ellipsometry, the basic of ellipsometry is really to be able to determine the refractive index, not the thickness. It's not done for that.
Okay, thank you very much.
Please.
Yep.
Thanks, bro. Thank you very much for your last presentation. I already put my questions on the chat that I will just start now. It relates to the distribution of your tungsten within the VO2 structure. Since you're starting with the layers, it's more like a multiple layer system. How is the distribution when you're picking up at about 400? Is it 450 or 400?
400.
How do they monitor the distribution?
Well, we didn't monitor it before and after annealing.
Yeah.
So I cannot.
Yeah,
I cannot tell you what was going on before annealing, because the people from the CEA, they gave us the samples after annealing, which is normal, because if you really want to get the right structure, you need to anneal the samples. And so I cannot tell you how it was changing from the multi-layer structure to the doped one. But as I was saying, I was unable to see any specific signature of the tungsten in the diffracted pattern. So it means that, in my opinion, it means that the tungsten was distributed quite uniformly inside the film. Maybe there were some clusters, but very small ones. so that you could not see them on the scattering pattern. Because if they are very small, the bragg peak of the tungsten would be extremely broad, and we didn't see anything like this.
Yeah, because you can have a scenario where the distribution is towards the surface, or it's away from the surface, or it's diffusing on both sides.
Yes.
Towards the bulk and towards the surface. So we don't know now which one is affecting.
I don't know. I don't know. I cannot tell you.
But you can leave us with one sample. You can try the real-time RPS here. Real-time RPS. At least it can give us an indication as to where the distribution is going, whether the atoms are migrating to the surface or towards the bulk, or on both sides. Yes. In a real time.
But I don't have the answer to this question so far. But maybe the people at the CEA, they have done quite a lot of experiment on those films, and they can answer it. I will ask them, and I will go back to you.
Try and see whether we can, our system can.
All right. Okay. Thanks.
Any other questions? Okay. Thanks for taking time for this nice webinar. If there's no question, I think we just finish it up.
Yes, I just have one thing to say. Guillaume is going to leave around 4 o'clock. So for those of you who want to discuss with him, it's the right time. And I will be here until beginning of December. So there is plenty of time to discuss with me if you want. But for Guillaume, it's the only opportunity that you have. Well, maybe he's supposed to come back. So, later it's possible by email.
Okay, thank you very much for attending. All right.
So thank you very much. Thank you very much, everybody. Thank you, Mahmoud, for organizing this this presentation. Goodbye.
Bye.
Bye.